Hi, everybody. This is the first lecture from chapter 27 on circuits. So in this chapter, we're going to talk about basically resistive circuits. We'll also talk about a resistor with a capacitor a little bit. But the first thing we want to do is look at how do we deal with resistors. And by resistors, I mean really anything that has a resistance. It could be a light bulb, could be a toaster, could be whatever device is in the circuit, or it could be actually little elements of circuits that are called resistors. And basically what those resistors are meant to do is to limit the current or change the value of the current in the circuit. And we'll see how that works here. But in today's lecture, what we want to talk about is resistors in series and parallel. And so we've talked before about resistors or capacitors in series and parallel. It's sort of a similar thing, but as we'll see, the addition rules are just the opposite. But let's first of all talk about resistors in series. So we're going to be using Ohm's law, V equals IR, right? The voltage across a resistor is current times the resistance. Assuming all of the resistors in our circuits obey that law, we can get some rules for how to add resistors in series and parallel. So in series, again, what I mean, we have our circuit here. We'll take our battery, say it has 10 volts, and we've got a single loop in the circuit. And each resistor is in series, one right after the other. So first thing you'll notice possibly is that in a series circuit like this, the current, I, is the same through each resistor. So there's only one current in the circuit, and it goes all the way around. I'm just going to call it I. Right? It's everywhere in the circuit, all the way around it, through the battery and through both resistors, and it's the same value. But the voltage across each resistor may be different. So if I took a voltmeter and I put my probes on each side of the resistor, I might get a V1 for the resistor 1 and a V2 for the resistor 2. They may be different if the resistances are different, but they are related through something called Kirchhoff's loop rule, which says voltage must add to 0 around a closed loop. So the point is, if I go around a loop in a circuit, go out and then back to where I started, a closed loop, the voltage has to add up to 0, which in our case means that the voltage across the battery, I'd say that's a voltage gain, right? It's adding energy to the circuit. Across each resistor, I'd call it a voltage drop. So it's kind of a minus voltage, a change in voltage. So if I add this V minus IR1 minus IR2, or minus V1 minus V2, they have to add up to 0, which ends up giving this relation, right? Voltage from the battery has to equal voltage across resistor 1 plus voltage across resistor 2. Now, plugging in Ohm's law, we define an equivalent resistance. Now, this is the resistance that the battery senses. It kind of, in some way, adds the resistors together to get a total resistance, and that's our Req. But according to Kirchhoff's rule, or Ohm's law, right, V equals IR, so we have IREQ equals IR1 plus IR2. Now, the currents are the same, so they cancel out, and I just get Req equals R1 plus R2. And there's our series addition rule. Anytime you have resistors in series, you just add the resistances directly together. And again, right, you could have a third resistor up here, maybe on this side. I would just have R1 plus R2 plus R3 and so on. So I could have any number of resistors in series, they just add together. So in our case, our equivalent resistance is 5 ohms, R1 plus 10 ohms equals 15 ohms. When you add resistors in series, they tend to increase the total resistance and lower the current in the battery. But we can calculate the current in the circuit now just by taking the voltage of the battery divided by Req, right? Again, just kind of using Ohm's law. And we get 10 volts over 15 ohms, or 0.67 amps. Now, if I wanted to get the voltage across each resistor, I just use Ohm's law again, separately for each one, right? V1 equals IR1, 0.67 amps times 5 ohms. That gives me about 3.3 volts. I've rounded a little bit. and V2 equals IR2, 0.67 amps times 10 volts, or 6.7 volts. And you can see if I add these together, they do equal the total 10 volts of the battery. So again, this shows the lower the resistance here, right, the smaller the voltage drop in the series circuit. It kind of makes sense. The less energy it uses up and turns into heat and things like that. Okay, so let's go ahead now and look at series in parallel. And in this case, it's very similar, right, to the capacitive case. I just created two loops now, one for R1 and one for R2. Now the thing about parallel circuits is that the voltage across each resistor is the same. And in this case, it's 10 volts. It's equal to the battery voltage. But the current may be different. And the reason for that is that the current splits, right? So I'll have a current going through from the battery through that part of the circuit, call that I, and that's going to split into I1 and I2. Now they do kind of come back around the circuit and recombine at this junction over here after they've split up at this junction. Now there's another rule called the junction rule for the circuits, and this is not from conservation of energy like our loop rule was, but it's from conservation of charge. I can't lose electrons as they flow through the circuit. So the current going into a junction must equal the current coming out. So in our case, we'll have I going in has to equal I1 plus I2 going out. And that's what I call the junction rule. So again, using Ohm's law, current is voltage over resistance. Define an equivalent resistance that the battery senses, right? I, its current over its equivalent resistance. That's going to equal V over R1 plus V over R2. Again, just using Ohm's law separately for each resistor. Now, the voltages are the same, so they cancel out in this case. And I end up with 1 over Req equals 1 over R1 plus 1 over R2. And that's my parallel addition rule. Now, it's just the opposite, right, of the capacitors. The capacitors in parallel add directly. So this is kind of what I mean by it being opposite. The addition rules are different for series and parallel for resistors compared to capacitors. Now, again, if I had a third resistor, I can go ahead and just add a plus 1 over R3 if it's in parallel. Well, let's do the calculations. In our case, 1 over Req is 1 over 5 ohms, R1. That's 1 over 10 ohms, that's R2. Adding these, I get 3 over 10 ohms. So I have to flip that, right? I've got the reciprocal here. So Req is 10 over 3 ohms, or 3.33 ohms. What you'll notice is, in parallel, the resistance actually, the equivalent resistance actually is lower than each resistor. And that's because to get current through each branch, I've got to add more current in the battery. So the battery actually senses a lower resistance when resistors are in parallel. Now, if I want the current in each one, I just take I1 equals V over R1, just use Ohm's law again, 10 volts over 5 ohms. So I get 2 amps in the 5 ohm resistor, and I'll end up getting 1 amp in the 10 ohm resistor. Again, it makes sense, right? I get more current if there's lower resistance. Now the total current going through the battery is going to be 3 amps, right? Again, using this junction rule here. So I get 3 amps in the battery. It splits into 1 amp going around the 10 ohm and 2 amps in the 5 ohm. Then it recombines back into the total 3 amp current down here. Now, there are some advantages to connecting things in parallel. One advantage is that, let's say I cut the circuit right here. It will not affect R2, right? I mean, it's still 10 volts across a 10 ohm resistor. The current will be the same. Now, what will be affected is, if I switch this off, well, this current will reduce. It will go from 3 amps down to 2 amp, or to 1 amp. Sorry, 2 amps. So every time I add something in parallel, I'm going to have to add more current from the battery. But objects in parallel are really not affected by the other objects. So in your house, right, you'll often wire different rooms in parallel. So let's say the circuit breaker went off for one part of your house, it would not affect the other parts. Now you do have also a main circuit breaker, which is set for this part right here to cut off the main current. And if that main current gets too large, it'll just shut everything down. How does it get too large? Well, maybe you add too many things in parallel, right? You turn everything on in your house, and it just gets a large current right there and snaps off the main circuit breaker. Also, the power company, that's what they want to know, is how much current you're using. You can get the power usage, right, again, by taking current times voltage. And that's what they're interested in, is that main power. Now, another question I could ask about these circuits, what if these were light bulbs? Which one is brighter? Now, you could use, at this point, power equals current times voltage to figure that out. But I'm going to let you think about that, and maybe I'll answer that here in another video. But hopefully that shows you how to add and do the problems where resistors are in series and parallel. And in the next video, we'll actually go ahead and do a more complicated circuit where we combine several resistors in series and parallel and get the current in each part of the circuit.